Today we're trying to record or prove a proposition on the natural numbers that's equivalent to this statement here, 108 raised to the n, where n is a natural number, minus 24 also raised to the n. Okay, this quantity, not really necessary here, but I'll go ahead parentheses here, is equal to some multiple of 7. We'll say 7k. Okay. This literally means this number minus 0 is divisible by 7, or this number minus 0 is equal to 0 plus a multiple of 7, which is this statement right here. Okay, and this is for all n natural numbers. We can say n equals 0 if you want to, n equals 0, 1, 2, 3, all the way out if you want. Now, again, a lot of people see this and they automatically opt for induction, but I think modular arithmetic is a little more principled. And let's get started by just considering a general, both of these are just general terms, integers raised to an integer power, natural numbers raised to a natural power. And so the binomial theorem turns out to be quite handy here. And y'all, I will say the binomial theorem holds for all n, right? It also holds, I think, for rational numbers, but it holds for all n, a member of n, right? So that kind of obviates the necessity of even considering induction. If this already handles all n, why mess with induction? Okay. So now also notice that this would be congruent to 0 mod m. Right? And why is that? That's simply because km, I hate to use the word trivial, it sounds condescending, but any multiple of m is congruent to 0 mod m. That's literally the definition of modular arithmetic right there, or divisibility. So you see each one of these terms that has, and notice this is a binomial coefficient here, n choose 1, n choose 2. This part right here is congruent to 0, the whole thing, because it's multiplied by something, just like in regular equality. All of these are congruent to 0, except for this very first term. Oops, this is a mistake right here. Let me erase that. That should be b to the n. Okay, b to the n, sorry. So you see all of these objects to the right are equal to 0 modulo m, so all that is left standing is b raised to the n. Now that's going to be quite useful if you reconsider our original expression here. So you see you can rewrite this as 3 plus 15 times 7, 7 times 15, 15 times 7, whatever. Okay, raised to the n power. Okay, and then also right here you would have minus 3 plus 3 times 7. All raised to the n power, right? You see this result right up here just says that this is congruent. The result that we just went through with based on the binomial theorem, that's going to say that this is congruent to 3 to the n minus 3 to the n, which is certainly equal to 0 and congruent to 0. Mod m. Mod 7, excuse me. We're using mod 7. You see these terms right here just go poof because they're multiples of 7, right? 7 times 15 is 105 plus 3 is 108. 3 plus 3 times 7 is 21 plus 3 is the 24, right? So you see we wanted to show that was true, and we did. It has been demonstrated. All right, folks, that is it. And again, I hope you liked it because, again, a lot of people just see an n and they've learned induction. It's their new tool and they want to use it. I suppose you can use induction, but it just seems so artificial here when you can appeal directly to the binomial theorem and get the job done. And just try some small numbers here. Let's see, just n equals 1 is an easy one to try. Already, if n is equal to 2, the numbers are too large, but 108 minus 24, and I'm just cheaping out doing the simple one here. 108 minus 24 is equal to what? Is that 80, 70, 84? That's equal to 84, which is equal to 12 times 7. Okay. And it just keeps on. It's much harder, but this proof says that continues to hold. And basically on a just basic multiplying congruence together type of result, you know, you can multiply congruences together over and over and over. That's just kind of a simpler way to think about it if you want to, which is really what the induction idea is. All right. But here the binomial theorem gives us something very, very concrete for all in, and it cleans it makes it a fairly clean problem. Okay. Thanks for viewing.